Welcome back, everybody. I hope everyone had a good weekend. Sadly, I don't have the exams graded yet. My meeting for my department ran a lot longer than I expected, so I ate up my entire Friday. But either way, we got some good, important stuff done in that meeting. Totally got some good stuff done. Talked about very, very important things that will never come to fruition, so that's great. But if I did, I would have had them done. I'm doing everything in my power to get them graded and handed back on Wednesday. So we left off last time talking about the implications, the biggest implication of the mean value theorem, which is the theorem that we're going to use a lot, where if a function's derivative is positive, that means that the function will be increasing. If its derivative is negative, the original function will be decreasing. And then if the derivative is equal to 0, the function will be constant on that interval. And then we kind of briefly went quickly over a proof of the reason why using the mean value theorem, saying that suppose that your function was positive and you took 2 points inside that interval, then there would exist c value between it, so that by the mean value theorem, f of x of 2 minus f of x of 1 was equal to f prime of c times x2 minus x1. And both those things are greater than 0, which means that f of x of 2 is greater than f of x of 1. And that is precisely the definition of increasing. So that is the proof of it. The proof of the less than case or the equal to 0 case are also very, very quick. And they are basically the exact same description. So find the intervals of increase or decrease of the following functions. F of x equals x to the fourth over 4 minus 5 halves x squared plus 2. So let's think about what we would need to do. We want to find out, since we want, okay, this is not going to work. You're still leaning. Yeah, I'm still leaning, and since we want to, God, I can't do it. I can't do it. Okay, maybe I'll find something else. Maybe I get a giant block, like just a giant thing to do it. Okay, let's erase this and try again. So with better handwriting. Since we want to find where f prime is greater than 0 slash less than 0 slash equal to 0, sorry, no, and f prime less than 0, what should we do? So that shouldn't be a period. That shouldn't be a period at the end there because we're going to add to it. But I want us to think about this. When the derivative, is the derivative going to be a linear function, meaning a line like 2x plus 5 or 8x minus 9 or something like that? No, that derivative is not going to be that. So it's nonlinear. And what we're trying to do is we're trying to find out where that function is positive and where it's negative. And one thing you might remember from Math 126 was the idea of a nonlinear inequality. Now, in 126, we were tasked with finding things like find where this is greater than 0. But when you were doing that, when you were finding the solution intervals to that inequality, you had to make a sign chart. And the sign chart told you where a function was positive and where it was negative. So instead of trying to find specifically where it's positive or negative, we're going to use a sign chart to find out those intervals. Since we want to find where, we'll make a sign chart. For f prime. I forgot to plug in everything. So we'll make a sign chart for f prime. And that will allow us to find where the derivative is positive and where the derivative is negative. So do you remember where, what we had to do with those situations? So just to briefly set the stage, when I had x times x minus 3 is greater than 0, what did you do first? Find the x values where Yeah, well, no, specifically equal to zero. You wanted to find the dividing values, the what I like to call the VIPs. I know they're not important points, but they're not points, they're values. But Viv doesn't have the same ring to it as VIP. But specifically, it's not just where it equals zero, because what if I had this in Math 126? You'd write the VIPs where x equals 0, 3, and -2, right? That's what we do, and then we set up a sign chart. That's interesting. Those are where the expression equals 0 or where it does not exist. Have we learned anything recently where we need to set something equal to 0 and find where it equals 0 and where it doesn't exist? Critical values. Critical values are the spaces where the derivative equals 0 or does not exist. And that's exactly what these are for this situation. So, um, step one is going to be find f prime and its and the CVs. The SCVs actually more specifically. So the critical values will be like if we have a critical value, it might be a relative extrema. If we remember that there's that theorem that says if you have a relative extrema, then it's a critical value of the function. But SCVs still play a role. Semi-critical values that aren't critical values still play a role. So we're going to find both of them. So in this case, it's a polynomial. So the semi-critical values are all critical values because the function is defined everywhere. So in this case, f prime of x will equal x cubed minus 5x. Okay. And so we'll set that function equal to 0 / DNE. And I'm going to factor out an x right from the get-go. And everything is a difference of squares if you want it bad enough. So x squared minus 5 can be split up further. So this becomes x times x plus the square root of 5 times x minus the square root of 5 equals 0. And therefore, we have all of our critical values: 0, negative square root 5, and positive square root 5. And those are our CVs. And they're all critical values because the function is a polynomial and it will exist at any of those values because polynomials exist everywhere. That's step one. Find the derivative, set it equal to 0 to find the places where the derivative equals 0. Because once you've had those, you can create a sign chart to figure out where the derivative is positive and where the derivative is negative. So step two is going to be make, very, very scientific term, make a number, no, not number. Make a sign chart thingy. Very, very scientific, I know. A sign chart thingy is not exactly a sign chart because the way I draw these ones is a little bit different because I add a little extra thing to it to make sure I distinguish between the two of them. So I'm going to draw a number line. And we're going to draw a bunch of tick marks, 3 tick marks in particular. 1 for each critical value. Okay. And as a helpful little tip, I always recommend this to my students. Put your critical values, put any of the numbers that are important, put them above the number line. Because down below, you're going to be using test values, and then it gets kind of confusing if all the numbers are there. So we've got negative square root 5, 0, and square root 5. Okay. Now, this is a way that I set up any random sign chart. That's the way I set up any sign chart that I'm trying to find. However, I want this one specifically to correspond to the derivative. The reason why I mention that is very, very soon we'll have one with the second derivative as well. And it's very, very useful to break them up and make sure you can identify which one's which. So I'm going to put an f prime here. To remind myself, this is my f prime sign chart. This isn't my f sign chart. This isn't my f double prime sign chart. This is my f prime sign chart. This is my derivative, first derivative sign chart. Then I will plug in x equals, okay, what's the number less than negative square root 5? You can always use your calculator to get an approximation. Square root 5 is roughly 2.2-ish. So negative 3 would be fine, but you can do negative 30. You can do negative 3,000 if you want to, but negative 3 is fine enough. Then x equals negative 1, x equals 1, and x equals 3. And so the way that I've always done this, and this is what I'm going to do this first time so you can see how my method works. If you like a different method or if you've learned a different way of doing these things, awesome. Kudos to you. Keep doing it your way. I'm going to do it differently. So I'm going to highlight this x in red, this x plus 5 square root in green, and this x minus square root 5 in purple. Not in purple. Let's do orange or blue. Blue's fine. So when it comes to finding a sign chart, I don't care what the number is. All I care about is whether the thing is positive or negative. So really all I'm looking for is the sign of each piece. Because if we know the sign of all the things multiplied together, if we know each thing's sign, we can figure out what the overall sign is by just counting the number of negatives. An even number of negatives results in a positive, an odd number of negatives results in a negative, and so on and so forth. So when I plug in negative 3, the x factor in red, that's going to be negative. The x plus square root of 5. You got negative 3 plus square root 5. Square root 5 is 2.2-ish. So much. If like ish. And so negative 3 plus 2 point something, that's going to be negative as well. And then negative 3 minus square root of 5, that's of course going to be negative. So all three factors are negative. That's 3 negatives, which is a net negative. So it's negative here. The derivative is negative there. And so this is what I draw. That's a normal sign chart, but this is a sign chart thingy, very different. And so what we're going to draw is a line going downwards to symbolize to us that tangent lines will be now having negative slopes here, right? If our derivative is negative, and our derivative can represent the slope of a tangent line at any given point, then if it's negative there, then we have negative sloped tangent lines. And our function will be decreasing. So that arrow, that down arrow is telling us two things. It's telling us our tangent lines are negative. Our tangent lines have negative slopes, rather. And it tells us that our function is decreasing there. It's going down. Then at negative 1, the red factor of x is going to be negative. The green factor, now you have 1, a negative 1 plus 2 point something. It's going to be positive. And then negative 1 minus square root of 5, that's going to be negative. But here we have a net of 2. We have 2 total negatives, which is a net positive. So the derivative is going to be positive here. And that means we're increasing. We'll have positively sloped tangent lines along this area, and our function will be increasing by the theorem above. And so on and so forth. So when we plug in 1, now the red factor is positive. The green factor is now positive. But the blue factor is still 1 minus 2.2-ish. So the blue factor is negative. And that's 1 negative, so that's a net negative, and we're decreasing again. And last but not least, when we're at 3, every single factor is positive. Since there's no negatives, the result is a net positive, and it's increasing. So these arrows do a lot more than just tell us increasing, decreasing, as we'll find out very, very soon. But that's how we work through this one. Now, a couple things, couple caveats to mention. First and foremost, did anybody remember the multiplicity trick from Math 126? Where you can figure out what the next sign of the next area is going to be based on the multiplicity of the zero or the root. Did anybody remember that? It's okay if you didn't. These are all multiplicity 1, they're odd. So add an odd multiplicity, you will cross through, meaning that you will go from one sign to another. And so do you notice that every single time I go through a 0, it changes sign? Whereas an even sign, an even multiplicity, it bounces. So at an even multiplicity, you'll stay on the same side. So if this had even multiplicity, or if this had even multiplicity, it would stay negative, but it's not. It's flip-flopping. That brings, so if you want to use the multiplicity trick, if you remember it, awesome. But otherwise, most students in my calculus courses, they just decide to do a sign chart like standard style, and that's fine. If you want to use the multiplicity trick, though, you'll definitely get an ooh or an ah from me because that's clever. But it's not a big deal. It saves you maybe 2 seconds, so it's not a big deal. What I will try and caution you, though, the reason why I mentioned that whole multiplicity trick is because a very common misconception that students have is they assume that once they found the first piece, they can just keep alternating because this one alternates. A lot of the times they do alternate, but that's not guaranteed. You have to do a sign chart and you have to test each interval or use multiplicity. One of the two to make sure you find the sign. It is not sufficient to just test one and then assume it's going to flip-flop. Okay? So, based on this information, we're only asked to find the area intervals of increase or decrease. So any places where the derivative was positive, it'll be increasing. Any place where the derivative was negative, the function will be decreasing. So it's increasing from parenthesis negative square root 5 to 0, comma, square root 5 to positive infinity. And it's decreasing from negative infinity to negative square root 5, comma, 0 to square root 5. That is our answer. Older textbooks will use a union symbol instead of a comma to write the intervals of increase and decrease. And that's because there was you probably heard about it in the news. It was pretty big. It was in like the 2008. So it was right around the market crash. It was a big deal, actually. It happened in Italy. There was a big mathematics education conference. Bunch of mathematics educators from all around the world were coming to Italy to discuss different properties of mathematics. And then the question of whether or not you should use a union or a comma in when you're talking about increasing and decreasing, that came up and that got heated to the point where it was a massive bloodbath. About 15 mathematicians died. 17 people died after the fact from bleeding out, and then 2 or 3 were left over. The Highlanders won. You know, it's Highlander rules. Last one standing, there can only be one. And that last person standing actually ended up saying, no, it should be commas. And that's why we use commas now. True story. Not really. It was a very, very heated debate. It really was. People got nasty during that debate. But the argument was that increasing, decreasing should be met with a comma. Because if you say a union symbol, you're saying it's increasing the entire time. And looking back at this graph, if I said it's increasing from -1 to 0 union from 2 to positive infinity, from 2 to about 2.75, this piece is below this piece. So how can it be increasing throughout if it stops increasing here and then goes down? That was their argument, is if you said a union, it would mean that it would be like this piece right here would have to be, this piece right here would have to be up here in order for it to be true. That was their argument, because otherwise you're saying it's increasing on that entire chunk, and that's not necessarily accurate based on the definition. So that's the reason why it's using a comma. If you use a union, I'm not going to mark it down, but I just want you to know that the convention is to use a comma. And then some textbooks will say that you should use brackets for the number portions of these increasing, decreasing, and some textbooks are wrong. It's just a fact. It doesn't make any sense to say you're increasing at a specific endpoint. That doesn't make any sense. So you can use brackets. I'm not going to stop you because that's what some textbooks have taught, but it should be parentheses. So, anyways, any questions on Oh, that was step 3. Write your answer. Step 3. Find the increase and decrease. Any questions on that? Okay. So part B is going to be the same question. Find the intervals of increase and decrease. Now, here's a little thing to put a little pause before we start going derivative crazy and having a lot of fun taking derivatives and all that jazz. We need to know the domain, because if we start plugging in numbers, and so here's a good point. Let's find the derivative together, and note that the domain is 0 to positive infinity, right? X squared, that's defined everywhere. X is defined everywhere, but natural log of X is only defined for numbers strictly greater than 0. So our domain is 0 to positive infinity. If we take the derivative, which we can write dy dx, why not? That's going to be 2x minus 1 minus 3 over x. Now, the reason why I wanted to mention the domain, because if you're looking at this, where is this function defined? What's the domain of that function? There's only one issue. 0. You can't plug in 0 into that value, right? You can plug in negative numbers and have no problem, but the context matters. This is the derivative of this function. So this function has restricted the derivative's domain to 0 to positive infinity. How can your derivative be defined somewhere that your function isn't? Does that make sense? So that's the reason why we have to take into account the domain, because this function is only defined for positive numbers, which means that our derivative of our original function is only defined for positive numbers. It can't magically exist elsewhere, even though it could in theory. If you're just looking at it purely as its own entity, that thing is defined everywhere except for 0. But its context is that it is the derivative of this function. So it has to be defined for only positive numbers. That's going to play a role when we take our sign chart. I want you guys to find the critical and semi-critical values of this function. So go ahead and, set it equal to 0, find where it doesn't exist, and write it as something that you can find the zeros of, the critical values. People watching the recording, you should have your first hint right now of what to do. And then I'm going to pause the recording. I should have done that first. So try and get all your critical values and then proceed. So you should get the potential semi-critical values of 3/2, -1, and 0. However, I've crossed out -1 and 0. They're not SCVs. They're not semi-critical values because they don't even exist in the derivative. The derivative is only defined for numbers strictly greater than 0. So we probably should even mention that, by the way. Therefore, y prime dy dx's domain is, well, this is even weirder to explain without set notation. is smaller than that, is potentially smaller than that. Never mind. I'd have to use set theory, and we don't have set theory in this course, so I can't really say it. But what I'm trying to say is that's the domain of y. And once you take a derivative, your function can get messier. And so once you take a derivative, your domain can get more restrictive. Case in point, just to bring this home, the cubed root of x to the 1/3. You don't need to write this down. That domain is negative infinity to positive infinity, right? That's the domain of that function because you can plug in whatever you want into an odd root and it always exists. But if you take the derivative, y prime, that equals 1/3 x to the negative 2/3, which could be rewritten as 1/3 square root, a third square root of x squared. Now that function, that derivative, its original domain, the domain of the original function was all real numbers. So that's a starting point for y prime, and then we pluck out any more problems that y prime has, and it has a problem at 0. So this one's domain is negative infinity to 0 union 0 to positive infinity because of the fact that f prime or y prime is not defined at 0. So the derivative's domain is always a subset of the original function's domain. Does that make sense? Does that have any questions? That subset means a set within inside it. So this interval is a subset of negative infinity to positive infinity because it's the same thing we've just nixed out 0. So anyways, point being is that the domain of this function starts off already. The derivative, it starts off with the potential of having 0 to positive infinity, and then it might get more restrictive. It doesn't. Good news for us, but either way, I'm getting sidetracked. I'm getting lost in the nuance. Back to the point. So -1 and 0, they are not actually SCVs because the derivative doesn't exist there. Not in the domain of y or dy dx. So the only semi-critical value we have is 3/2. But that's also a critical value because the function is defined there. Its domain is all real, all positive numbers. 3/2 is a positive number. So it's both a critical value and a semi-critical value. Now we make our sign chart. And so instead of making, so I'm going to start off by drawing a line just like normal. But I'm only going to draw an arrow on the right-hand side, and I'm going to draw a parenthesis on the left-hand side and write 0 here. Because there's no need to test any numbers less than 0. Our domain is 0 to positive infinity. So we can't do anything to the left. That's just wasted work and confusing work because we'll get wrong answers. We'll get additional places where the function doesn't exist. So we'll stop at 0, and then we just have 3/2, which is 0.5. And this is a derivative sign chart thingy. So we'll write dy dx or y prime, depending on what you want to do. And we'll do a test value of x equals 1 and x equals 2 because 3/2 is 1.5. And so we'll plug that into the derivative, ideally in its factored form so that we can just look at the signs real quick. It's not wrong to use an unfactored version, but it's going to require more work, especially if the numbers get too obnoxiously large. So if this was 200, trying to plug in 200 into the unfactored form is a lot more of a daunting task than plugging it into the mini factored form. Plugging in 1, you'll get negative times a positive over a positive. That's a net negative, and our derivative will be decreasing. Our derivative will be negative, so our function will be decreasing. Plug in 2, and everything becomes positive. So the net result is positive. So it's increasing there. So it's increasing from 3/2 to positive infinity, and it's decreasing from 0 to 3/2. So John Doe student would like to draw for numbers less than 0, but John Doe student's wrong here. Itching. Either way. Okay. Any questions on that one? All right. All right. So we have essentially done what I'm going to put on this next page, which is the first derivative test. We've basically, by drawing these arrows, when some people introduce this topic, they don't draw these things. They just write the minus sign and the plus sign. But I want you to draw them because it will help us with the first derivative test to visualize it. So the first derivative test says let f be a differentiable function and x equals c be a critical value of f. It didn't say semi-critical value because this is going to talk about relative extrema. In order for your function, your original function, to have a relative extrema, it needs to be a critical value. Semi-critical values that aren't critical values, your function doesn't exist there, and that's a problem. So if f changes from positive to negative, so I'm going to draw this above it, from positive to negative, then f has a, what do you think? If your f prime, if your derivative changes from positive to negative at x equals c, that means you went from increasing your original function. So notice that it says the original function, then f, original function. What do you think it has? Do you think it has a relative maximum, a relative minimum, or nothing? That arrow chart is trying to help you. It's kind of making a hill, isn't it? So it's going to be a maximum. Has a relative maximum. If your function keeps going up and up and up and up, and then at C it decides to go down, 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 you've got a relative extrema. You got a relative maximum. And the same thing is true for if, well, similar but different, if f changes from negative, going downhill, to positive, going uphill, what do you notice? You got a relative min. Then the last one is if f's sign does not change, f prime, excuse me, if f prime sign does not change, if it goes from positive to positive or from negative to negative, if it stays that way, then there's no relative extrema. Then f has no relative extrema. At x equals c. And so, as a small reminder about jargon in mathematics, a relative maximum or a relative minimum, that is a coordinate point. The relative minimum or maximum value is the y value at that maximum or minimum. And then where it occurs is its x value. So for example, just to get the terminology right, let's say my relative maximum is the point 3 comma 5. The way you say that in 3 different ways is that the relative maximum is the point 3 comma 5. It has a relative maximum value of 5, and it occurs at x equals 3. That's the terminology. So just whenever I say for location, I'm talking about the actual point, just so we're clear. So that's going to be relative in a little bit. So that's the reason why I had you drawing these. So what you're looking at this one, you'll notice this function has a relative minimum at 3 halves because the derivative goes from negative to positive. So your function goes from decreasing to increasing. So let me use the pointer for people watching the recording. Decreasing to increasing. It makes a valley. It makes a little divot at the bottom. This function has 3 relative extrema, one at -5, one at +5, and one at 0. The ones at -√5 and +√5, those are going to be relative mins because the function will go from decreasing to increasing, and then 0 will be a relative maximum. That's why we draw the arrows. So Find the intervals of increase and decrease along with the x values of any relative extrema. So here, I'm not looking for the location of the relative extrema, and I'm not looking for the relative maximum values or minimum values. I'm just looking for the x values. So our function is x to the fourth over 4 plus x cubed over 3 minus 8x squared minus 16x. Let's take the derivative, because we're going to have to find where this function is increasing or decreasing, which means we need to find the derivative. So f prime of x would be x cubed plus x squared minus 16x minus 16. And we'll find where the derivative equals 0 or does not exist. So that's 3. That's going to be x cubed plus x squared minus 16x minus 16 is equal to 0. It doesn't, there's not going to be any places where it does not exist, but I still write it to remind myself that that's what I'm doing. I've had plenty of students, you don't need to write this statement here on the side. This is for our note-taking purposes, and that's it. So that is a quadnomial. So that requires factoring by grouping. And it will factor by grouping nicely. The other way to do it was with the rational zeros theorem, but I don't want you to do that. That requires using some division. I don't need that in my life right now. So we're going to split it down the middle and factor it. Factor out the mini GCFs, and you should find that there's a common binomial factor. So I factor out an x squared, the mini GCF of the first two terms, I get an x plus 1. And if I factor out a negative 16 from the second set, I get an also x plus 1. So that factors, that x plus 1 factors out. We'll be left with an x squared minus 16. And x squared minus 16 is a difference of squares. So we have that this factors finally to x plus 1 times x plus 4 times x minus 4 equals 0. If you don't remember factoring by grouping, by the way, do not panic. I usually don't put those on exams. I usually make it something that is factorable nicely. Like maybe you'll have to pull out an like a GCF of an x. Like maybe like on an exam you might see this x cubed plus x squared minus 16x equals 0. So that you can factor out an x first, so that you don't have to worry about factoring by grouping because it's such a niche topic. Just something to easily, quickly factor. But either way. So our CVs, and they're all CVs because this is a polynomial, it's defined everywhere. Our CVs are x equals -1, -4, and +4. So we'll set up a sign chart. And this is for f prime. So I need 3 lines. And those are -4, -1, and 4. And we'll test values. X equals -5, x equals -2, x equals 0, and x equals 5. The thing I tell my pre-calc students is whenever you get the chance to use 0, 1, or -1, use it. Because those are the quickest numbers to use to calculate things. They're very, like, especially 0, to calculate sine. Not sine, S-I-N-E, but S-I-G-N, like the sign of a term. Sign of a number. Okay, so go ahead and fill in that sign chart, and then draw your pluses and minuses and your up arrows and down arrows, depending on the situation. And the one thing I love about this section while you're working through this is that it's very, very intuitive. What would it mean, like positive increasing, negative decreasing? It's not like opposite things. It's not like, it's very, very intuitive that plus means increasing, negative means decreasing. So that is our sign chart. It goes negative, positive, negative, positive. So sometimes I'd like to draw some little things to remind myself. So we have 2 mins and 1 max. Because it goes from decreasing to increasing, that'll make a little valley. And then it goes from increasing to decreasing. That'll make a little hill, and then decreasing to increasing. So another valley. So if we're going to write the answer, it's increasing from parenthesis -4 to -1, comma, 4 to positive infinity. Decreasing from -infinity to -4, comma, -1 to +4. And there's relative max at x equals -1 and a relative minimum at x equals -4 and +4. And that is our answer. Okay. Any questions on that? Nothing? This is all jiving. We're all vibing. Say, as the kids say. Good, good. We're all vibing. Okay. So I've got two other examples here, both with their own interesting situation. And it's a lot like the crux of these problems is the algebra. So specifically part 3.3.4, and I want to go through that one. So what I would like you guys to do is I want you guys to find the derivatives and simplify them for both of these problems, and then we'll start working through the rest of it. But notice that it said for part 3.3.3, it says, and the location. Location means I want the coordinate point. So go ahead and find the derivatives. I'm going to pause the recording, find the derivatives for both parts. So these are the derivatives you should get. And I said during the pause that I chose these two problems for two specific reasons. So now that we've simplified, and remember, we're simplifying because we're going to be using these derivatives for something. My rule of thumb is that if you need to use your function for something, or if you need to use what you've found for something, simplify it, otherwise leave it unsimplified. So if we're going to find where g prime is equal to 0/dne, I notice that there's a negative x that can be factored out. And this is x plus 6 over x cubed, or x to the fourth equals 0/dne. One of the x's will cancel. And so we have negative, and I'm going to highlight that negative in red, x plus 6 over x cubed equals 0. From equaling 0, you get x equals -6. And from x cubed, that's going to be dne. So you get x equals 0 from the dne portion. You get -6 from the numerator. That's where the derivative would equal 0. And you get the place where the derivative does not exist, which is 0. Are they both CVs? Take a second. Are they both critical values, or is one a critical value and one a semi-critical value? Option. One's the yes, JT said it correctly. One of these is a critical value, whereas one of them is a semi-critical value. -6 is a critical value. 0 is a semi-critical value because it doesn't. The original function does not exist at 0. So we got. I'm just going to rewrite it below. X equals -6 and 0. This is a CV. This is an SCV because g of 0 does not exist. But you'll see here in just a moment why, and this problem here also illustrates why I made the distinction, why I even brought up that they needed to be talked about. So now that we've done that, now that we found the critical values, we can set up a sign chart and find where the function's increasing or decreasing and so on and so forth. So we'll set that up all the way up here. And this has to do with our derivatives. So we're at g prime and we have two values. So -6 and 0. And so we'll plug in like x equals -7, x equals -1, and x equals 1. Those would be good choices. So this problem is twofold. I want to remind us, we factored out a negative. That negative sign always plays a role because the only thing that changes signs are the negative numbers. So that negative sign sticks around every single time. So make sure you always have it. Don't forget about it. It's always there. It affects things. At -7, x plus 6 would be negative. And x cubed would be -7 cubed. That's -343. So that's 3 negatives. So it's decreasing there. The function is decreasing from -infinity to -6. Plug in -1. Now the x plus 6 factor is positive over x cubed. That's going to be negative. That's a net positive. And then if you plug in 1, you get a positive over a positive for the remainder portion of it, and that's a net negative. Okay. So if you just look at the, so does anybody have any questions about the minus sign playing a role? Because keep that in mind, minus signs do play a role when it comes to sign charts. You'll notice that if I have a 5 here, just a 5, if I change this to a 5, I never actually include it because positive numbers don't do anything to signs. But as soon as I have a negative number, I have to keep it in mind. Okay. So it is asking me for the location, not the x value, just the x value. And that's one of the reasons why I like being asked for just the location, because it can tell you immediately that one of these things is not actually a relative maximum. 0 is not a relative maximum. Because g of 0 does not exist. It's not a relative maximum because g of 0 does not exist. It's actually where this function has a vertical asymptote. This function has a vertical asymptote at x equals 0. And a horizontal asymptote at y equals 0, but that's neither here nor there. So that's the but notice though, the reason why I talked about semi-critical values though is they play a role in the sign chart. If we ignored the 0, if we ignored this, let me use a, if we ignored this, we would think that this function was defined, it was decreasing from -infinity to -6 and increasing from -6 to positive infinity. But that's not true. The semi-critical values play a role. Even if they don't actually end up giving you any relative extrema, they do affect the sign chart. That's why I had the distinction. I know they didn't really make any sense in 3.1, but they matter here, and I wanted us to get comfortable with them then so that we'd be fine with it now. So, but -6 is a relative min. And g of -6 is equal to -6 plus 3 over -6 squared, which is -1/12. Okay, one more thing on this one before we move on. Just as a reminder, I'm plugging it into the original function. If I'm asking for the location of relative extrema of the function, I'm talking about the relative extrema of g. So I have to plug it into g, not into g prime. You'll see that if you plug it into g prime, you get 0, which is not surprising. That's where the derivative equals 0. But normally you don't need to write what I've written in red. You can just write g of -6 equals -1/12 if you want. but I'm doing it here to remind us that this plays a role, and you need to be careful about it. Is it really? Yeah, it's 112. So we need to remember that when we're finding relative extrema, we're plugging it into the function to find the actual location. So at the end of the day, we're increasing from -6 to 0, decreasing from -infinity to -6, and from 0 to +infinity. And then we have a relative min at -6, -1/12, and a relative max, max none. Or NA, or no relative max, however you want to write it, just to symbolize that there is no relative maximum. Yes, JT.
So if 0, 1 existed, we would just plug it in the same way to find the y value. Right?
Exactly right. So the reason why I found what g of -6 was because I needed to find the location. I needed to find the y value. So I plugged in the x value to get the function value or the y value. If the function did exist at 0, we would plug it in to find the location of a relative maximum. But the function did not exist at 0, so it does not have a relative maximum. Any other questions on this one? So there's a point to finding semi-critical values, even if they don't give us any relative extrema. They give us the shape of the graph. So, on to this one. This one, I had this one specifically to teach you how to be a little clever. So if we want to find the critical values, which this is a polynomial, right? If you expand out z minus 1 squared times z plus 3, that will expand out to a cubic, and it will be a polynomial. So all of its SCVs are critical values, all of its semi-critical values are critical values. And you could, in theory, you could sit down and FOIL this, because what we're going to have to do is we're going to have to make h prime equal to 0 and find out where it doesn't exist as well. So that's 2 times z minus 1 times z plus 3 plus z minus 1 squared equals 0. Now, I think I'm going to change this in the future. I think I'm going to make this better. I'm going to make it z plus 3 to the 4th power, or something like that, to illustrate something here. I could FOIL it. I could. And it'll give me a quadratic, and it won't be too terrible to do. It's not the end of the world to factor this. But if these were nastier numbers, it would not be fun, and it would be very difficult to go through with it. So I'm going to be clever. I'm going to notice that both terms, there's this first term that's a product of stuff, and the second term, they both have at least one factor of z minus 1. So we can factor that out from the start. I'm going to underline that. That's a common factor, so we'll factor that out front, z minus 1. And then we've got 2 times z plus 3 plus z minus 1 equals 0. Now it's a much faster calculation. Instead of having to do 2 times the foiling of z minus 1 times z plus 3 plus the foiling that I have to do for z minus 1 squared, instead I can factor the z minus 1, and then I've just got some small bits of distribution algebra to take care of. So that's going to be, this is going to be 2z plus 6. So adding those things together, we've got z minus 1 times 3z plus 5 equals 0. And that gives me the CVs, z equals 1 and -5/3. So let's make it, I want you guys to go ahead and finish the problem. Notice this one just says find the x value. So we don't need to find the relative extrema locations. But I want you to set up your sign chart and find the critical values. Or find the relative extrema, if there are any. That goes for you people watching the recording. Sorry if you're still working through it, but I want to get to the break here. So our critical values are 1 and -5/3. We'll set up our sign chart. You should get positive, negative, positive for the different pieces. for your h prime. So that means that you're increasing, then decreasing, then increasing. So we've got negative infinity to negative 5/3 and 1 to positive infinity for the places where the function's increasing. Negative 5/3 to 1 for the places where it's decreasing. And then it has a relative maximum and a relative minimum. It has a relative maximum at negative 5/3 and a relative minimum at 1. If the question asked me to find the location, all I would need to do is plug that into h of z, and then I would find the y value, and I get to write the point. Are there any questions on that? The extra practice problem is a very, very good one, but let's take our break. Let's come back at 10:13. All right, people watching the recording, do some guided meditation.
Wait, was
Spreading the light at the beginning. Okay, so this is one of my favorite problems. It's a very, very conceptual one, and you'll notice that I haven't done any y scaling at all. And I haven't done any x scaling, but I should have. It's just I didn't have it at the time. I want you to plot 1, 2, 3, 4, 5, 6, 7, 8 tick marks on the x-axis on each side. Six or seven, or eight, 7 to 8. You get 7, that's fine. Okay. So you're given the graph of g, but you're not given anything about its function. Now, it's not a polynomial because it doesn't follow the end behavior. It's a weird function that I've kind of created. Actually, I've made it a monster out of different piecewise functions and trying to make it look like it's perfectly differentiable and perfectly continuous, but oh well. So we don't know how to find we can't find the derivative because we don't know what this function's equation is. So there must be some way to get around it. And so here's the first thing. Step 1. Because I need to find the graph of g. Now, what I can tell you is I can find the zeros of g prime. How would I be able to find the zeros of g prime? Remember, you can think of the derivative as a slope of a tangent line, right? That's one thing you can do, but you can also think of it like a function. So if you can find the places where the derivative equals 0, those will give you the zeros of the roots of the derivative. And those correspond particularly to right here, and right here. So step 1 is to find places where tan slope equals 0, because that means that g prime of a equals 0, which implies that g prime will have an x-intercept there. So we have an x-intercept at -2 for g prime. We have an x-intercept at 4 for g prime and an x-intercept at 6 for g prime. So -2, 4, and 6. We know those values. Okay. Does anybody have any questions on that? So let's break that down one more time while you're plotting those points. The derivative, if you plug in specific values, or if you draw the tangent lines, that will be the value of your derivative at that spot. So in particular, at x equals -2, you have a horizontal tangent line, which means that g prime of -2 is 0. Thinking about that in function notation, that's going to be on the x-axis. G prime of -2 equaling 0 means you have the point -2. So let's even write that down. Let's write that down. That's a good point. So g prime of -2 equals 0, which implies that -2 comma 0 is on the graph of g prime of x. Okay. That gives us a start. That gives us 3 points, but 3 points is not a graph. So how do I find the rest of it? So I'm going to color code this. I'm going to color code from negative infinity all the way to -2. And then from -2 to 4. And then from 4 to 6. And then from 6 onwards. I'm going to bring this down a little bit so I'm tall enough to touch it. I'm not that tall. So I'm going to use this black marker for a second in just a moment. And people watching the recording, I'm sorry you don't get to have this experience. So if you have questions about it, please feel free to talk to me after class. So what step 2 is going to be is to work on each piece by looking at slopes of tangent lines, of tan lines, to determine G prime of X's values. I'll let you write that down and then we'll explain what I mean. Is G prime of -6, is it positive or is it negative? G prime of -6. Is the slope of the tangent line positive or negative there?
Negative.
Negative. So G prime is negative at -6. But it's roughly like it's almost 0, right? It's a very, very very shallow line. And actually, as we get closer and closer to negative infinity, it just gets flatter and flatter until it's basically 0, but not 0. So as we move along the graph, negative slope, slightly more negative, slightly more negative, slightly more negative, slightly more negative, until about, I'd say, 3. When it gets the most negative it's going to be on this blue piece, and then it starts getting less negative, less negative, less negative, until it becomes 0. So on this first segment, it's actually going to look very, very similar. It's going to start off being very close to 0, but negative. So I'm gonna highlight a spot right here in, let's do black. At 3. At X equals approximately -3, G prime is the most negative it will be on that segment. Most negative it will be on negative infinity to -2. And then it starts leveling off. So thinking about it once again, I'm going to say this out loud once you finish writing that. So the slopes of your tangent lines at like negative infinity, they're basically 0, but they're slightly negative. They're slightly negative. Like we're talking like a slope of -0.1. And then it starts getting more and more negative, but not very much. It's like probably 0.5 right now, maybe point like at best. And then it gets more negative. Now it's at about a slope of like -3/4. Then at 3, it gets to be about a slope of -1. And then it starts becoming less negative and less negative and less negative until it hits 0. So the first piece of the graph should start off below 0 until it hits and gets slightly more negative until it hits 3. And then it starts becoming less negative until it reaches 0. Now, we'll do the red piece. Bring it down just a little bit more and zoom in. All right. Yes, JT.
Sorry, once it gets -3, is it like supposed to be like a curve up?
Yeah, it's supposed to be curving up. Then, from 2 to -4, starting at -2, the derivative, the tangent line is 0, meaning that the derivative is 0 there, and which is why we're at the purple dot, we're at 0. But now at like negative 2 point or negative 1.5, it's positive, but not very positive. More positive, more positive, more positive until about one-ish. It's hard to tell exactly where. But then it starts becoming less negative, or sorry, less positive, less positive, less positive, and zero. So the derivatives values based on those tangent lines, they should get larger and larger until they hit about one, and then they need to start becoming less positive, and they hit zero. Then on the green piece, we start off at zero with a tangent line of zero, meaning that G prime is zero at negative at 4. Then it's pretty steep, but it's not nearly as steep as it is about 4.5-ish, where it's the most steep it's going to be, but it's negative. Negative tangent slopes, meaning the derivative is negative there, meaning it's below the x-axis. Then it becomes less negative, less negative, less negative, zero. So on that green segment, it should dip down and then come back up and become zero. And then on the orange piece from 6 beyond, starting at 6, it's zero. So the derivative is zero, which is why we have that x-intercept at zero. And then more positive, more positive, more positive, more positive, more positive, more positive. It just keeps getting more and more positive as we go along. The slopes of those tangent lines will keep getting more and more positive, meaning that our function, our derivative, which is the slope of the tangent lines, will get more and more positive. So it should start to go up like that. And that's how you graph it. It's a pretty fun problem. And when I was graphing these ones, I didn't so you're trying to do it with your pencil, and your pencils are probably a little too big. So what I was doing when I was taking this on the exam in my calculus course, I was looking at my hand while I'm taking it, and there's like 300 people in this lecture, and I'm this one going like this, like that. And so I looked like a weirdo, but I got the points on it, and they did. So they can deal with it. Anyways, so that's what it should look like. Pretty cool. Pretty cool that we can create the graph of a function, even if we don't know, like the graph of a derivative, even if we don't know the equation of the derivative. So that is G prime's graph. Now that one. So in Math 126, I told you how to get a second date. This is how you stay married right here. This the one. This is how you if your marriage is going downhill a little bit, starting to worry, you have 2 kids and they're causing a rift in the marriage. The spark is gone. Bust out this problem, solves everything. Seen it happen with my friend Chris Proudfoot. They were going through a problem. Their daughter is 9 months old right now. He busted out this problem. I showed him during a Magic Gathering little hangout. Not that I've ever played. I don't play. I just watch. So brought that up, and now they're thick as thieves now. Okay. Anyways, neither here nor there. So you probably have been wondering, what is the point of finding a second derivative, right? We learned in 2.3 that there are such things as higher order derivatives. There's the second derivative, the third derivative, the fourth derivative, and so on and so forth. And the question may become, why do we want to take more derivatives? And there is a physical application behind it. The second derivative gives you acceleration. I believe the third derivative gives you torsion in physics, and the fourth derivative gives you torque, or jerk, I think is the name of it. I'm not a physicist. But there is a cool graphical interpretation of the second derivative. The third derivative and beyond is kind of hard to describe and not very useful. There's a video by a person I think named Michael Penn who talks about what you could use the third derivative for graphically, but I've watched it and it's very convoluted and unnecessary. So regardless, the second derivative is important. So a function is what we call concave up if it curves upwards. Imagine if you had like a stick and you start bending it to try and make a smile. If you try bending it upwards, it starts to make that smile shape. That's what it means to be concave up, and concave down as if you're bending it downwards. So any place where you change concavity is called an inflection point. And so what we're going to do is we're going to look at this graph to maybe discover something about the connection between a function and its derivative and its second derivative. So between here and here, which I'm going to mark in red, I'm going to highlight in red. From here until about 0, it's concave down. From 0 onwards, the curve is bending upwards. Like it's going down, but still it's like it's the left half of the bend upwards. It's concave up from that on that segment. And then so 0 is an inflection point. All right, it's not exactly 0, it's pretty close to it. I'm going to put it right about there. That's the inflection point. Okay. So that's what we have. And then I've also graphed the derivative, right? And so what I want you to notice, the inflection point is right up. I mean, like I didn't draw this perfectly, but the inflection point would be right around 0.25. So that's right here. What do you notice about a tangent line to the f prime there? What would the slope of the tangent line be? 0, right? So this is a very, very technically, we need to think about this a lot. This is a tangent line to f prime. So what is the slope? Where does the slope of the tangent line to the tangent function, to the derivative, come from? Let me say that one more time with more clarity. Where does the slope of the tangent line to the derivative come from? We get we get tangent lines, we get tangent slopes from the derivative of a function. So this is the second derivative being 0. So slope of tangent line to f prime to derivative, let's say derivative, to derivative is 0 at inflection point. Okay. So that's important to know. And then if we look at the place where it was concave down, it was concave down from about negative infinity to that inflection point. So this segment right here, what do we notice about the derivative to the derivative? The derivative to the derivative will be the slopes of the tangent lines to the derivative. So let me say that one more time. This is weird. This is technically difficult to understand at first. A tangent line here, it would get its slope from the derivative of this function of f prime. So the tangent line slopes for f prime's function are coming from the second derivative. So what I'm saying here is that the slopes of tangent lines to df dx are negative. And then over here, this is going to be that the slopes of tangent lines to df dx are positive. Write that down. Let's once again, let's think about this because I still see a bunch of confused faces, and I think that's completely valid. So we have to remember the connection between f prime and f double prime. The second derivative is the derivative of the derivative. So if you're looking at the graph of the first derivative, the slopes of tangent lines to that graph of the first derivative, the slopes of the tangent lines to the first derivative come from the second derivative. So that's when I'm going to write down here. Slopes of tangent lines of df dx come from its derivative, aka f double prime. So, point being, looking at this graph, the places where the original function f, not f prime, not f double prime, the places where the original function is concave down, the slopes of the tangent lines to f prime are negative, meaning that the second derivative is negative there. Whereas where the function is concave up, the original function is concave up, tangent line slopes to the derivative are positive, meaning that the second derivative is positive. And in particular, at an inflection point, we see that the tangent line to the derivative function, the first derivative, the tangent line to the first derivative is 0 there, meaning that the second derivative is 0 at an inflection point. So that allows us to have a little more information. This theorem isn't called the first derivative test or anything like that. This is much like the next one. It says, suppose that f is a twice differentiable function. That just means that its second derivative exists. Then if f double prime is greater than 0, then f, the original function, is concave up. If f double prime is less than 0 on that interval, then your original function is concave down. And as you can imagine, by the way, the reason for this, the proof of this fact comes from the mean value theorem. Once again, if you'd like to see the proof of it, I'm happy to show you, but in the interest of time, we will continue onwards. Then the last thing is that a function has an inflection point at x equals a if and only if f of a exists and f changes concavity at x equals a. There's a little bit more that needs to be mentioned. Technically speaking, you need to have that f is continuous as well. But that is kind of guaranteed by the fact that f is differentiable on that whole interval. If f is differentiable, then it's continuous on that interval. So that's not really needed to be mentioned, but it is like in weird situations in mathematics, you can have that happen. But for us, that'll never happen. So for an inflection point, you need the function to exist there and for concavity to change. Much like with a relative extrema, right? You need the function to exist at a critical, like in order for it to be a critical value, the function needs to exist there. So find the intervals on which f is concave up and down along with the location of any inflection points. So very similar, but slightly different. Now we're trying to find it here. We need a sign chart for f double prime, because we want to know where the second derivative is positive and where the second derivative is negative. So we'll take the first derivative, simplify if need be, because we're going to be using the first derivative to find the second derivative. But there's not much needing to be simplified. F prime of x is equal to 4/3 x cubed minus 9x plus 7. And I'm not going to bother setting that equal to 0 because I'm not interested in where it's increasing or decreasing. If this question had said, find the intervals on which it's increasing, decreasing, concave up, concave down, and location of inflection points, then yes, I need to set this equal to 0 to find where it's increasing or decreasing, but it just wants concavity. So we'll find the second derivative. which is going to be 4x squared minus 9. And if we want to find the places where the second derivative equals 0 or does not exist, then that's going to be setting 2x plus 3 times 2x minus 3 equal to 0, because 4x squared minus 9 is a difference of squares. And that gives me x equals negative 3 halves and positive 3 halves. Now, if concavity changes at those two values, then those will be inflection points, because f is a polynomial, which means it exists everywhere. So if we find that concavity changes, those will end up being inflection points. So first we need to make our sign chart. And so this time, instead of making it for f prime or for g prime or h prime, this is an f double prime sign chart. So negative 3 halves to positive 3 halves. And I'm going to write f double prime here instead of f prime. And we're going to create the sign chart like usual. So let's do x equals negative 2, x equals 0, and x equals positive 2, because negative 3 halves is negative 1.5. And so we'll plug them in, and we get a negative times a negative, which is a positive. So we're not going to draw an up arrow here, because that's what we were doing for the first derivative, to signify that the function would be increasing. Now we're talking about concavity. So when we're positive, we're feeling positive, and we got a smile when you're concave up, and you've got a smile. You should be curving upwards. You have a bent up situation. When you plug in 0, you get a positive times a negative, which is a net negative. And if you're feeling negative, you're feeling down, and you've got a frown. You're concave down, and you've got a frown. And last but not least, at 2, you'll get a positive times a positive, which is a net positive, and you're feeling up again, so you've got that smile on your face. Right? You can put 2 dots to make it a smiley face if you want to. Concave up. So at negative 3 halves and at positive 3 halves, concavity changed. So both are inflection points. Let's use red. Both inflection points. Inflection points. Because concavity changed. And f exists there. So let's plug those into the original function, because this question was asking for the location. And that will be, so f of negative 3 halves is equal to 1/3 times negative 3 halves to the 4th minus 9 halves times negative 3 halves to the 2nd power plus 7 times negative 3 halves. Sorry, I'm running out of space. And that equals approximately negative 19.36. And f of 3 halves is approximately 1.64. Once again, I'm showing that we've calculated it in the function. We're not plugging this into the derivative. We're not plugging this x value into the second derivative. We're plugging it into the function, because we want the inflection points to the function, not to its derivative, not to its second derivative, and so on and so forth. So concave up was negative infinity to negative 3 halves, and from positive 3 halves to positive infinity. Concave down was in between those two things, from negative 3 halves to 3 halves. And we had inflection points at negative 3 halves, comma negative 19.36, and 3 halves, 1.64. I do this every semester where I think, oh, Phil, you're going to be able to get through 3.3 and start 3.4 in the same day. You're going to totally be able to do that. It never works out. 3.3 is such a monstrous area. So let's see, we got that. Okay. We got 4 minutes, right? Okay. So, good trig example. Everyone's favorite, I know. From negative pi over 2 to pi over 2. That's a weird interval, but we can do it. Let's just take a deep breath and remember we have all of our trig. We all got that memorized. I've seen it time and time again that you guys have proven to me that you guys know your trig, so I'm glad about that. So I don't have any concerns with your ability to do the trig here. Right? Right, yes. So this one's just asking for concavity and x values of inflection points. We'll take the first derivative and the second derivative, and then we will come back and finish this problem. So P prime, first derivative would just be 4 minus 2 secant squared of x, because the derivative of tangent is secant squared. All right. And then the second derivative, P double prime of x, would equal negative 4 secant of x tangent of x times, oh, no, sorry. Negative 4 times secant of x to the first power times secant of x tangent of x. So simplifying that, that's negative 4 secant squared of x tangent of x. And I think that's where we'll leave it off for today. I want you to understand why that's true. So think about that. I'll give you a hint. It has to do with the chain rule, but you should verify it yourself why that's true, why it's negative 4 secant squared tangent of x, or secant squared of x tangent of x. And then when we come back next time, we'll set this equal to 0 and find where it doesn't exist to create our sign chart for our P double prime. All right? Yes.
What's going to be
On the quiz. That's right. What are we going over? What did I say? On 3.1 only. So finding extreme like absolute extrema. That's it. 3.1 only, okay? If you have any questions, feel free to email me. Otherwise, you guys have a great rest of your day. I'll see you guys on Wednesday for the quiz and to finish this stuff off. See you then.